Hey there, happy Monday. We, believe it or not, only have 2 more weeks left for this semester, this year. Things are rushing in on us here. A great job on the exam. I got those graded. Mrs. Barabo is going to pass those out back to you guys. I think overall you're feeling comfortable with those integration techniques. We're going to use some of those integration techniques, not a lot of them very heavily, in this last chapter that we're going to do here, chapter 6, and I'll get into that in a little bit. Just a review for this week. This is a normal week for us. Monday, Wednesday, Thursday. There is no quiz on Thursday. I didn't give you guys anything for that. Next week, I'm going to flip things around a little bit. We're going to have a lecture on Monday. The last lecture, we were supposed to have the last lecture on Wednesday and then a review on Thursday. I'm actually going to switch those. So we do the review a little earlier. And then the last lecture, I'm going to actually be there to answer any review questions you guys have, to go through some last lecture material. There's one last topic that we do need to cover. So we're going to go over that as well. And then the following week, our exam is on Wednesday. And I believe it's at 8:05. It's in the morning on Wednesday. So just 2 more weeks, really 5 more lectures, but only 4 of them are likely to be on the exam. Just to let you guys know, the exam itself, it will be cumulative. It's going to be over all of the material from the course, but the emphasis is going to be on chapter 6, the stuff that we've done now. But I will give you hints of other things that we've done. The major ideas, not any little nitty-gritty detail stuff, but some of the major stuff. So we'll go over that when we do review next week on Wednesday. All right? So I just want to review, before we jump into chapter 6, I wanted to review just a little bit about L'Hopital's rule. So this is section 7.7. L'Hopital's rule. Okay. Now, if you remember, we talked first when we were talking about L'Hopital's rule about indeterminate forms. And hopefully that makes sense now what an indeterminate form is. An indeterminate form is a limit form that when you try to take the limit right away, in other words, when you try to plug in, you get a result that you can't tell what's going on and you have to do extra work. It doesn't mean, indeterminate form does not mean that you can never figure out what the limit is. It just means you can't know right away what the limit is, right? So in other words, if I have a fraction, for example, if I had a fraction, a function over a function, and the top function I knew went to 2, and the bottom function went to 1, I would immediately know what the limit is. That is not an indeterminate form. The limit would be 2. But if the top function went to 0 and the bottom function went to 0, I would not immediately know where that function, where just with that information, I do not know where this function is going. I have to do further work in order to figure out where we're eventually headed, okay? So those are called, when that issue comes up, when you have to do further work, not just plug in, that's called an indeterminate form. Okay, and the indeterminate forms that we talked about were, the division ones were 0 over 0 and some sort of infinity over some sort of infinity. Okay, plus or minus infinity over plus or minus infinity. The multiplication ones that we talked about were 0 times infinity. The subtraction ones that we talked about were infinity minus infinity, and the power ones that we talked about were 1 to the infinity, 0 to the 0, and infinity to the 0. Okay? And we talked about how when you have one of these forms, then you can do L'Hopital's rule on something like this. And L'Hopital's rule says, if you have one of those forms, then rather than doing the limit of the top over the limit of the bottom, you look at the limit of the derivative of the top over the derivative of the bottom, okay? And we write a little L' H over the equal sign just so we know when we're doing that, somebody can follow our work. You can only do that, just as a reminder, you can only do that with indeterminate forms that look like that. Either 0 over 0 or infinity over infinity. You cannot do it in other cases. In the case of these other situations, you have to do some manipulation to get it in this form of 0 over 0 or infinity over infinity, so that eventually you can use L'Hopital's rule. So for multiplication, we talked about putting one factor on the bottom, never natural log, right? For subtraction here, we talked about getting a common denominator. For this power rule, we talked about setting it equal to y and taking the natural log. I want to do one example of that, homework problem number 43. Okay, so this is 7.7, number 43. Thinking maybe that's not dark enough. Okay, and that one said, limit as x goes to infinity of x to the power 1 over x. Yeah, that's, I'm going to switch colors here. Hopefully you guys can see the green that I'm going to use. Okay, so the point is that I want to figure out what the limit of this x to the 1 over x is. And what we talked about was, when you have a function to a function, many times that's a very difficult thing to work with. We want to try to get one of those functions away from another one. So what we do is we set that problem aside completely, and we instead first look at the natural log of y instead of just y. And the reason we do that is that we can take this power and move it out into the front. So natural log of y in this case equals 1 over x times the natural log of x. And what we're going to do is, instead of looking at the limit of this original problem, we're going to look, which we called y, we're going to look at the limit of the natural log of y. And that's going to give us information to be able to get this limit later. Okay, so if we look at the limit of the natural log of y, that's the limit as x goes to infinity of 1 over x times natural log of x. Well, 1 over x goes to 0 when x goes to infinity. Natural log, here's natural log, goes to infinity when x goes to infinity. So we have this, now this multiplication indeterminate form. So now what we're going to do is we're going to just turn this into a fraction, and it's very naturally going to end up as a fraction. I just make that 1 over x into an x on the bottom. And now the top and bottom are both going to infinity. So we are now at a place, this was all of our work, got us to the place where we can use L'Hopital's rule. Okay. So if I do that, the derivative of the top is 1 over x, and the derivative of the bottom is 1. Okay, and now I reevaluate. When x goes to infinity, the top goes to 0 and the bottom goes to 1. This is not an indeterminate form anymore. It's very clear what this is. This is 0 over 1, and that is 0. Okay? Now, you'll be tempted to say, okay, so my answer is 0. No, that's the answer to this problem. So now the answer to the original problem, what we have to do is we have to remind ourselves that y is equal to e to the natural log of y. Remember, e and natural log are inverse functions of each other. So if the natural log of y is going to 0, then this whole thing is going to e to the 0, which is 1. So the answer to this original problem is 1. Now, I will put at least one L'Hopital's rule problem on the exam in 2 weeks. I'm not going to give you one of these power problems, though. So I only gave you one on the homework because I wanted you to see it. I wanted you to work with it a little bit. If you take further classes, this could come up later. You need to have at least seen this before. But I'm not going to give you a problem on the exam with that is one of these power ones. Okay? All right. So let's jump into chapter 6 now. This is our last chapter. And chapter 6 is on applications of integration. For us, the applications are going to be looking at length, area, and volume. Okay? Length, area, and volume. Now, since we're talking about integration between length, area, and volume, the one that seems to make the most sense to immediately jump toward is area. So that's why section 6.1 is about areas, but it's about areas between curves. And I'll explain what I mean by that in just a second. Okay. So in this section, we're actually going to have, there's about four different things that are going to show up, but they're all variations of the same thing. They're all variations on one theme. Okay. Let's start with, let's start with the basic idea of what we're going to do. So the first type of problem that we're going to see is we'll have a function up here that I'm going to call f and a function down here that I'm going to call g, and 2 points a and b, and I want to find the area between f and g. This thing does not work. I want to find the area between f and g and between x equals a and x equals b. So in other words, the way that I've drawn this, I would want to find this area. Okay? This is the first type of question. This is the main type of question that we're going to want to answer here. Now there's a couple of ways that we could come up with a formula here. Okay, so notice, first of all, let me just point out that here f is bigger than or equal to g, and that's important. We'll come back to that later. And we want that between x equals a and x equals b. Okay, so the first way that we could do this is that we could say, okay, the way that we did integration before is we would chop this interval up into a bunch of pieces, and we would take rectangles where, in this case, those rectangles are going to be sitting here within this area, and we just have to figure out what the height of the rectangles are and what the width of the rectangles are, right? So what we'll notice here is that if I cut this up and call each of these, let's say they have width delta x, then the area that I'm interested in here is going to be the sum of rectangles where I need height times width, right? And the height, I'm not going to get too picky here whether I'm using right or left endpoints or whatever, but you're going to notice that the height of each rectangle is the height of f at some point minus the height of g at some point. The height here is the difference between f and g. And the width is delta x, right? And then the area, technically the area isn't this, the area is the limit of these rectangles, right? So I'm going to take the limit as n goes to infinity, and the area becomes, remember what we did is that sigma, which stood for sum, the letter s, in the limit it becomes elongated s, and I'm going from a to b, and the function, we just write the function in there, and the delta x becomes a dx. So one way that I could think about coming up with what this area should be is that it's going to be the limit of rectangles where the heights are f minus g, and the width is delta x, and when I take that limit, that's just f minus g. The other way that you could think about, so this will be our formula for the area between these two functions, and that should probably makes some intuitive sense. The other way that I can think about this is if I were to redraw it, you don't have to redraw this on your paper. If I wanted the area between these two curves, if I wanted that area right in there, this area right here, what I could imagine doing is I could take this whole area, just the area under F, which would be this thing, right? That's the area under F, and then just subtract off the area under G, which would look like that. And that would give me the blue area right there. But that's exactly F minus G inside that integral if I brought those two integrals together. So either way of looking at it gives me that formula. So I'm going to always take, what you'll notice here is the area between two curves is always the integral of the upper function minus the lower function. Okay? And then you've got some limits of integration there, right? So what we're going to do is we're going to practice this a little bit with an example. And as we do this example, there's a couple things that I'm going to emphasize here that are super important. All right? Okay, so let's take, for example, I've got the functions y equals x plus 2 and y equals x. And I want that between x equals 0 and x equals 1. Okay. The very first thing you're always going to do with these problems is you're going to draw the graphs. Okay, you're going to need to draw the region. And that means that you either need to know what these functions look like or you have to get your graphing calculator out. Okay? So if you want to have your graphing calculator out, that's fine. You'll be able to have that on an exam while you're doing homework. That's not a problem. For these two functions are pretty simple. Okay, if you remember, x squared looks like this. And x squared plus 2 is going to go up 2. So basically, I'm just going to go up 2 and draw x squared. And then for the function x, that's just going to be this right here. And now I want that between x equals 0 and x equals 1. So that means I want that region right there. For each of these problems, it's super critical that you draw both functions and then identify what region it is that you're trying to integrate. So you need to draw the graphs in the region that you're trying to find the area of. Okay, the second thing you're going to do, I'm going to leave a space here because when there's something we're going to come back to later when we see a slightly more complicated version of this. There's one extra step we're going to need to add in here. But second thing we're going to do is we're going to set up the integral. And what I mean by setting up the integral in this case, what I'm going to have to do is, you can think of, if you want to think of, it depends on which of these versions you want to think of. It's actually helpful to think of the rectangle version. You've got a bunch of height times width. Okay? So we're going, the area, we're going from 0 to 1. And we need to add up the height of those rectangles times the width. Now the width is dx, right? We've got a little change in x there. But the height, I mentioned, is upper minus lower. So this is one of the critical reasons why you have to have these two functions drawn. You need to know which one is higher and which one's lower. In this case, the higher one is x squared plus 2. Minus the lower one is x. Okay. So that is the setup for our integral. Our height is upper minus lower. Okay, upper function minus the lower function. And the width is dx there. And then the third step is easy. What you would probably guess, you're just going to integrate. So now we're just going to integrate this function, and we should feel pretty comfortable doing this now. So we've got 1/3 x cubed plus 2x minus 1/2 x squared. And I'm going to go from 0 to 1. All right. Now when I plug in 1, I'm going to have 1/3 plus 2 minus 1/2. When I plug in 0, I just get 0. So that part, it's nice that that goes away. So I'm going to have, let's put everything in sixths here. So I'm going to have 2/6 plus 12/6 minus 3/6. So 14 minus 3 is 11/6. And that's my area there, 11/6. Hopefully that makes sense. Let's take a look at another example here. These examples aren't too complicated. The key thing here is to make sure that you're drawing the picture correctly. Okay. Let's just take a look at another example here. Well, I think for the most part this makes a fair amount of sense. You're going to do upper function minus lower function and then integrate. Let's look at how this might change a little bit. So the second scenario is where they're going to give you two functions, but they don't tell you an x and a y region. Sorry, an x, two x limits where they're going back and forth. So let me give you an example here. So what if I said, find the area of the region between x squared and x. And I didn't say between 4 and 6. So if I said between 4 and 6, what you would do is you would draw. Let's just do that example here real quick. Between x equals 4 and x equals 6. All right? So here's x squared. Here's x. All right? And then eventually when we get out here to 4 versus 6, this is not exactly to scale, but that's okay. Okay, from 4 to 6, this is the region that we're talking about here. Okay, so the first thing I do is I draw what it looks like. X squared and x from 4 to 6. All right, and then I set up my integral. So in order to do that, the area is going to be from 4 to 6. And I need to take my upper function. Well, I'm going to take height. Each of these rectangles that shows up in here. Each of these rectangles that shows up in here has a height and a width. Now the width is easy here. The width is dx. The height is the difference between these two functions, so I need to know which is the upper function, which is the lower function. The upper function here is x squared, and the lower function is x. So that is my integral that needs to get set up. And then I just actually do the integral. So, so the integral of x squared is 1/3 x cubed. The integral of x is going to be 1/2 x squared. And then I plug in 6, and I plug in 4, and I do that. I'm not going to take a bunch of time to do that. But hopefully that makes sense. So if they give you two functions and those x limits, that's how we're going to compute how that works. Now, the type of problem that I want to describe here kind of in this next part is what if they say, give me the region bounded by or enclosed by these two functions, and they don't give you any x values here. They don't say between x equals 4 and x equals 6. They just say, give me the area of the region bounded by those functions. When they do that, what they mean is that these functions are going to cross. So in this case, x squared and x are going to cross, and they're going to cross in such a way you can ignore the axes just for a second. I'm going to kind of just dot those axes so you're not actually looking at them. Okay? You need to think through what is the area that's finite that these two functions bound, that they kind of enclose. And in this case, between x squared and x, it's these two, it's that area right there. So without giving you an x equals a and an x equals b, there's still an area that they're talking about. So the way that we start a problem like this, we still draw the graph and draw the region that they're interested in. Now, we're not interested in this region because this is not a finite region. It's an infinite region. Same for this, this. Okay, we're interested in this region right here. But the extra step that we have to do that we didn't have before is we don't know necessarily where that point is and that point is. So we have to find the intersection points. And that's sort of this maybe 1A step here, is we may have to find the intersection points. We have to find where these two functions intersect. Now, if you know those functions, you can probably guess that they intersect at 0 and 1, right? And sometimes you can intuit these, and it's not too hard. You can say if between 0 and 1, you can just move forward. But if you can't tell that, the way that you get intersections between two functions is you set the functions equal and you solve. Okay? The way that you get intersections of two functions is you set the functions equal to each other, and then you solve. Okay, and solving typically means bringing everything to one side and factoring. So in this case, if I factor out an x, I get x times x minus 1. And the only way that equals 0 is if either this thing is 0, so if either x is 0, or if this thing is 0, so x is 1. So that's our 0 and our 1. So there's going to be some times, I'll go over at least one other example, where you'll have to figure out where those intersection points are. Right? Once I have those intersection points, then I start in the same way that I was doing things before. So thinking again of a rectangle here, my total area is going to be the sum of those rectangles from 0 to 1, and it's going to be the height of those rectangles times the width. Now, again, the width is dx, and the height is going to be the bigger function minus the smaller function. But here's where you have to be careful. That's why you need a picture. With between 0 and 1, the x function is actually higher than the x squared function. So you would need to actually make sure that you're taking x minus x squared and not the other way around. If you happen to flip it, what you're going to find is that the answer that you eventually get will be negative, and that tells you did something wrong. Areas between curves in this section, all of your answers should be positive because we're talking about a positive area between two functions. Okay? And now you just go ahead and solve your integral. So you're going to do 1/2 x squared minus 1/3 x cubed from 0 to 1. That's 1/2 minus 1/3 minus 0, which turns out to be 1/6. Okay. So the only difference with this kind of problem is that you have to draw the functions and recognize what area is included there, and then figure out where the intersection points are so that you can move on with the rest of the problem, setting up the integral. let's try another example here. Okay. Let's say that I want the region bounded by or enclosed by, you'll see that either one of those is language, x squared, y equals 1, and x equals 2. All right, so what I do is I do x squared. Well, let's just do, I'm even going to erase the, sorry, I'm going to modify. I'm going to erase the x equals 2. Just x squared, y equals x squared, and y equals 1. So here's y equals x squared. And y equals 1 is right here. So the region that you should see, that's, again, just kind of, don't worry about these axes. They're not functions that we're concerned about right now. So I don't really want you to think about those. The one region that's enclosed here is this region. Okay. And again, you can likely, if you've worked with these functions before, you can likely guess where these two intersection points are. But if you can't guess, what we're going to do is we're going to set those functions equal to each other and solve them. Okay. So we're going to set x squared equal to 1, bring the 1 onto the other side and factor. And x squared minus 1 factors as x minus 1 and x plus 1. So you get x equals 1 here and x equals negative 1. Alternatively, you could have taken the square root of both sides right at the top and make sure you have your plus or minus 1. That works in this case. The reason that I'm pulling everything to one side and solving is that in most cases it's not that simple and you do need to actually pull everything to one side and solve. Okay. So now that we have that, this is going from negative 1 to 1. So thinking of an example rectangle here, then my area is going to go from negative 1 to 1. And I'm going to add up the height of those rectangles times the width. Okay, and the height, this is where I have to make sure I have the right function on top. The upper function is 1, and the lower function is x squared, and the width is just dx. Make sense? And then you go about solving that problem, and I'm not going to get into that right now because you know how to do those types of problems. So, okay. The third thing that can happen here is that you can actually get multiple regions that are being talked about, not just one. So here we had one region, but we could end up with multiple regions that are being described, okay? So let me give you an example here. Let's find the region bounded by the two functions y equals x cubed and y equals x, okay? All right, I want you to take a minute and just draw those functions, y equals x cubed and y equals x. Okay, take a minute and draw both of those functions, and then compare your picture with your neighbor's picture. Okay, here's what you should see here. Okay. X cubed looks like our disco man, right? There's x cubed. And then here's the x function right here. And again, ignoring these axes, because that's not part of what's supposed to be bounding this region, what you'll see is that there are two sections that are being described here, those two sections right there. Right? So far it's the same as what happened before, we just have multiple areas that we need to be concerned about. We probably need to next figure out where the intersection points are, so it looks like it intersects in 3 places. Okay. Those 3 places there. You can probably guess where that is, but let's just be careful and actually do the math. So if I set the 2 functions equal to each other and pull an x over, so I've got x cubed minus x, and I factor out an x, what's left is x squared minus 1. That can factor as x minus 1 and x plus 1. Okay. So overall, it looks like our places where these intersect are 0, 1, and negative 1 there. So it's going to be negative 1, 0, and 1 there. The only thing that's going to change when you have multiple regions is that you have to make sure that you do one integral for each of those regions, and you need to check and make sure which function is on top, because they may switch like they do in this situation, okay? So in this case, what I'm going to do, the 2 areas that I want, I'm going to set up as 2 separate integrals. So I'm going to go from negative 1 to 0, height times width, plus then a separate integral from 0 to 1, height times width. All right. So looking at this first region, the width here is dx, and the height, I have to take the bigger function minus the smaller function. Now the bigger function is the one that's toward the positive y direction. So the bigger function here is x cubed, and the smaller function is x. Okay, so that's that first integral. Plus, and when I do the second integral, again the width, if I did a rectangle here, the width is dx, but here the upper function is actually x, and the lower function is x cubed, so you notice they switch there. Right. So that's how I would set up that integral, and then I just need to integrate, but integrating those are pretty easy functions, so I can leave that to you to integrate. You don't actually have to do it unless you really have a desire, you really want to. One thing you'll notice, though, is that these 2 regions actually are the same. So you could drop one of these and do 2 times the other one if you wanted. That would simplify some of the work. You don't have to, but that would work there. Okay? So if you have multiple regions, make sure you do each integral separately for each one of those regions. Okay? It's not too complicated. It's not too bad. You just have to find those intersection points. Make sure you draw it correctly. Find those intersection points and do one integral for each of those regions that's sitting there. Okay. One last thing that I want to tackle, and I'll tackle this by giving you I'll give you an example problem. What if I wanted the region bounded by the functions, well, bounded by x equals y squared and x equals negative y. Now these are not functions, which is why I was careful in the language that I was using. But there is still a region that's here. So let's draw that region. Okay, if you're not comfortable with seeing this as there's 2 different ways to do this. One of them is to just solve for x. So you could write this as y equals plus or minus the square root of x. Right? Here's plus square root of x. Here's minus square root of x. Or you can tilt your head. This is y and this is x. You could tilt your head and notice that just like this is y equals x squared, x equals y squared looks like this, right? They're kind of inverse. They're inverse functions of each other. So if you had one, you could flip it and get the other one. Same thing here. Y equals negative x goes like this. If I were to flip that around, x equals negative y does the same thing. This is our second function there. All right. Okay, so now what I could do, here's the region that we're interested in. One thing that I could do, okay, you can kind of guess. I mean, we can set these equal to each other, but you can guess that where these are equal to one another is at 0 and 1. Okay, and one thing that I could do, this is y equals negative x, this is negative square root of x, this is positive square root of x. One thing that I could do is I could set up this area by thinking of it as a normal rectangle and doing the area from 0 to 1, height times width. And the width here is delta x or dx. And the height, I just have to make sure I'm getting the upper function minus the lower function. So the upper function is negative x, and the lower function is negative square root of x. Okay. So I could do that, and now I've got an integral in a form that I could do some work, get the answer. A different way to think about this, which is actually going to be very useful later on in the next couple sections that we're going to do, is rather than thinking of rectangles this way, they're not really functions, but the relations here, x equals y squared, which is the same thing down here, and x equals negative y, they're set up in terms of y rather than in terms of x, and I had to sort of change the problem to get everything in x's. Is there a way for me to do it in terms of y's instead of in terms of x's? Well, you can if you turn your head and you think about the problem this way rather than the problem this way. Here's what I mean by that. If you imagine your rectangles running in this direction, so a bunch of rectangles added up this way, rather than a bunch of rectangles added up this way, then everything would be in terms of y instead of in terms of x. Let me show you. So the area here, first of all, you have to figure out where these intersection points are. Now, in terms of x, they're from 0 to 1, but in terms of y, the intersections are at negative 1 and 0. So what I'm going to do, this is still always going to be height times width of these rectangles, but now my width, I'm thinking of my rectangles, everything's set up in terms of y, so I'm going to cut it so that my widths are dy or delta y instead of dx. And then my y runs from negative 1 to 0. Right? This is the negative part of y, this is the positive part of y. So I'm running from negative 1 to 0. And then the height of that rectangle in terms of y is the upper function. Okay, so higher y goes this way, lower y goes that way. The upper function here is negative y. The lower function is y squared. Okay. So that is the setup. I think of cutting it up this way instead of cutting it up this way because it's set up to be in terms of y. So my width is dy, and that y is going from negative 1 to 0. And then I just have to figure out my height by thinking of which function's on top and which function's on bottom. So this would be, these two should give you the same answer, but this is a little easier in terms of I don't have to solve and get square roots and other things. Everything's already set up in terms of y, so I'm going to think of it that way. Let's go ahead and solve this problem. Okay. All right, so integrating negative y, I get negative 1/2 y squared minus 1/3 y cubed. And I'm going to go from -1 to 0. So when I plug in 0 there, I just get 0. Minus, when I plug in -1, I get -1/2. If I plug in -1 here, I get a negative that counteracts that negative. I get plus 1/3. Okay, -1/2 plus 1/3 is -1/6, and then with another negative on the outside gives me a positive 1/6. Okay. So the key here is that I'm gonna, since everything's in terms of y, I'm gonna think of cutting everything up in the y direction. That, like I said, that's going to be helpful for us in the next few lectures that we have. Let's do one more problem here. Okay. Let you finish writing. So let's do the region. For example, let's do the region bounded or enclosed by x equals 3 minus y squared and x equals y plus 1. Okay. Okay, so for 3 minus y squared, well, y squared would be like this. Negative y squared is going to be flipped around like this. And then we're adding 3, so we're going to go 1, 2, 3. Remember, positive going up for y is this way. For a y function, going down is this way. So we're going to go 1, 2, 3. We're going to have 3 minus y squared, that's this function here. All right. And x equals y plus 1, if you want to, that's pretty easy to solve for y if that's a little easier for you to do. We start at -1, and we go up 1 over 1, so that's going to look like that right there. So this is x equals y plus 1. Okay. So now the region we want is this region right here. That's the region that's enclosed. Now before we do anything, I want you to notice if we were to take rectangles that are up and down like this, in this part of the region, the upper function would be y plus 1, or y equals x minus 1. And the bottom function, I would have to solve for x, and it's going to be nasty. But notice, over here, the upper function and the lower function are both this function, but probably the positive square root and the negative square root. So I'm going to have to, if I did this with x's, with vertical rectangles here, I would actually have to set up 2 different integrals, and that's actually going to be a big mess. I would not want to do that. So instead of doing that, we're going to do everything's set up nicely in terms of y. So I'm going to think of a rectangle going in the horizontal direction instead of the vertical direction. And what I have to do is first figure out where these intersection points in terms of y. And then I'm going to be adding up rectangles that are height times dy. So let's first get these intersection points, just like we normally do. So let's set those two functions equal to each other. Let's bring everything to one side. You can probably guess what these equal then. So we got a y squared, a y, subtracting 3, we get a negative 2. Okay, and then factoring, that gives us y plus 2, y minus 1. That's going to multiply to negative 2, but 2y minus y gives me a plus y there. So this part right here is y equals negative 2, and that part right there gives me y equals 1. So this is going to go from y equals negative 2 up to y equals 1. So my area, as I think about that area is going to go from negative 2 to 1 on the y-axis. All right, my height times my width, and my width in this case is dy instead of dx. And my height is the upper function, which is this function right here, 3 minus y squared, minus, give myself a little more room here, minus my lower function, which is y plus 1. And so then I just do my, calculate that from here. So that'll give me my area there. That make sense? So there are times when you want to slice it this way, and then you're going to be working with the dx times the height. But there are also times when it's smarter to slice it this way. And when you do that, you're going to have a width, which is dy, times your height, which is the difference in the functions in terms of y. Okay? So that'll be it for today. There's one more thing that I want to do in terms of area. I actually want to prove to you that what the formula for the area of a circle, because we now have the tools for that. But I want to hold off on that until Wednesday. So we're going to tackle that on Wednesday, and then we're going to start to talk about, now that we've done some area stuff, we're going to move into volume stuff. Right? So we'll tackle that on Wednesday. Have a great day.